Welcome to This Explainer. Today, we're diving into something literally invisible to the naked eye, yet it's the hidden powerhouse behind almost every piece of modern tech you own. We're talking about the microscopic construction sites of the future, microfabrication processes. If you've ever wondered how on earth we build complex machines so incredibly small that they make a grain of sand look like a boulder, well, you are in exactly the right place. Let's get right into it.
Okay, let's dive into this. At first glance, this layout, it almost looks like a blueprint for a massive city grid or some huge industrial complex, right? But what we're actually looking at here is a highly magnified view of a microfabricated device layout sitting right there on a tiny silicon chip. If you look closely at those intricately colored regions, you're seeing different material layers, metals, polysilicon, insulating layers, all stacked and patterned with just mind-boggling precision. The sheer complexity and the repetition of these tiny geometries shows exactly what microelectromechanical systems, or MEMS, are all about. We're literally integrating mechanical and electrical components into incredibly compact, microscopic devices.
Here's our blueprint for today's journey. We'll start with a welcome to the microworld, then explore photolithography, which is basically painting with light. After that, we'll walk through the step-by-step lithography process, check out etching to see how we sculpt the silicon, and finally, we'll wrap up with deposition, where we build layer by layer.
All right, Section 1. Welcome to the microworld, the foundation of modern tech. So, before we can really grasp the construction techniques, we need to understand the environment we're building in, right? We have to define what we actually mean by microfabrication, because this is the absolute foundation of MEMS technology. Simply put, microfabrication relies on techniques adapted straight from the semiconductor industry. But instead of just cranking out standard computer chips, we're using these highly accurate, super repeatable processes to create microscale mechanical structures right alongside electronic components, all housed on a single silicon substrate. We're talking about the precise control of material shape, thickness, and properties at the micrometer level. It's this exact repeatability that lets us reliably manufacture the highly complex sensors and actuators we rely on every single day.
Moving on to Section 2, photolithography, painting with light.
Now, I want you to just think about this for a second. How do we actually create these tiny, precise patterns on a completely blank silicone canvas? You obviously can't use a standard tool, or even a microscopic pen. So how do you transfer a complex geometric blueprint onto a tiny chip? Well, the answer is as elegant as it is complex. We use light.
Take a look at that circular disc mounted on the precision stage right in the center. That is a silicon wafer inside a super clean room environment. See how the patterned surface is reflecting the light? That's because it's filled with numerous microstructures arranged in a grid. And that equipment hovering right above it, that's a semiconductor wafer processing system. Photolithography essentially uses this machine as a highly advanced stencil. By projecting light through a mask, we can literally draw those initial microscopic blueprints right onto the wafer. It's an amazing process that allows us to define features like microbeams, diaphragms, and electrodes with a level of accuracy and scalability that makes modern microfabrication completely possible.
Okay, Section 3, the step-by-step lithography process.
To really grasp how this works, we need to break down the chronological workflow happening right there on that silicon wafer. There are 5 core sequential actions that make up this stenciling technique. First up, we have coating, where we prepare the surface. Second is exposure, which is where the light actually hits the wafer. Third, we have development, to reveal our pattern. Fourth is pattern transfer, making the pattern permanent in the substrate. And finally, stripping, to clean up our microscopic workspace. Let's visualize exactly how these steps interact. Now, what's really interesting about this is how clearly the chemistry is mapped out for us. Starting right at the top, we see the coating stage. We've got our silicon substrate covered by a thin layer of silicon dioxide. And on top of that, we spin coat this uniform layer of a light-sensitive material called photoresist. Moving down to the exposure step, we align a mask over the wafer and blast it with ultraviolet or UV light. The mask acts just like a stencil. Now here is where you really want to pay attention. Look at how it splits left and right. The behavior totally changes depending on the type of photoresist we use. If we use a positive photoresist, over on the right, the UV light actually makes the exposed areas soluble. That means they just wash away during the next step, the aqueous-based development. But if we use a negative photoresist, on the left, the UV light actually hardens those exposed areas, so everything else washes away. Pretty wild, right? Once our pattern is fully developed, we move down to transfer, where we etch away that unprotected silicon dioxide layer underneath. Finally, the strip step removes any remaining photoresist entirely. And what we're left with is a precisely patterned silicon dioxide layer completely ready for the next phase of construction.
Next up, Section 4, Etching, Sculpting the silicon.
So we've got our pattern drawn out, but, a drawing isn't a mechanical device. We actually need to carve it out. If photolithography is our stencil, etching is our chisel. This is where we selectively remove material from the substrate to form cavities, channels, and those tiny mechanical beams. Looking at the two mechanisms side by side, we basically have two main chisels in our toolkit: wet etching and dry etching. Wet etching uses chemical solutions to literally dissolve the material. It's fantastic because it's simple and it's cost-effective. However, it's generally isotropic, which is a fancy way of saying it etches in all directions evenly, so it can be a bit less precise. Dry etching, on the other hand, uses plasma or reactive gases. Think of this as your high-precision laser chisel. It offers incredible control, high resolution, and crucially, it's anisotropic, meaning it is direction-dependent. If you need perfectly vertical sidewalls to build a microscopic canyon in your MEMS device, dry etching is exactly the method that makes that extreme precision a reality.
And that brings us to Section 5, Deposition, Building Layer by Layer. Okay, so once we've sculpted the necessary shapes into our foundation, it's time to put the chisels down and start adding material. Deposition is essentially how we lay down the foundational floors of our microscopic building. We're adding incredibly thin films of material, sometimes just a few nanometers thick, which is mind-blowing, to create structural layers, sensing elements, or conductive paths. We generally tackle this in two ways: chemical vapor deposition, or CVD, and physical vapor deposition, or PVD. With CVD, we introduce gases that react chemically right on the surface of the wafer, growing a solid film directly on it. With PVD, we're taking material and physically transferring it onto the substrate, using methods like sputtering or evaporation. Whether we're adding metals, oxides, or semiconductors, the quality and uniform thickness of these deposited layers directly dictate how well our final MEMS sensor will actually perform and how sensitive it's going to be.
So let's zoom out and bring this all back to why this actually matters to you. The precise sequential steps we've covered today, using photolithography to draw the blueprints, etching to sculpt the shapes, and deposition to build the functional layers, this is the hidden architecture of the modern world. This specific, highly controlled workflow is exactly how the tiny accelerometers in your smartphone know when you rotate the screen, and it's how the critical airbag sensors in your car operate with absolutely flawless reliability. The micro world is literally running the macro world.
Which leaves us with a really fascinating final thought. Today, we explored microfabrication, building at the micrometer scale. But, as we know, technology never stops shrinking. If these complex microfabrication techniques give us the power to construct entire mechanical cities on a tiny speck of silicon, what happens when we go even smaller? What does the next frontier of nanotechnology look like? That is the incredibly exciting frontier of micro and nano electromechanical systems. I really hope this explainer has sparked your curiosity about the invisible engineering all around us and left you hungry to explore just how small the future can get. Keep learning, and we'll catch you next time.